So it's my pleasure to welcome Ricardo Mendes of the University of Oklahoma, who will speak on rational homotopy of G-manifolds and the geometry of their orbit spaces.
All right, thank you for the introduction, Carolyn, and for the invitation to speak. It's a pleasure to speak in the seminar. I spoke once before, and I was looking up just now when that was, and I think it was like May 2020. I think I was maybe the third speaker, at least that's listed on the website there. So early days of the pandemic. So yeah, it's a pleasure to be back speaking here. Nice to see some familiar faces. And so today I'm going to be talking about this like recent, more or less recent preprint of ours about rational homotopy theory and how it interacts with group actions and the geometry of the orbit space of the group action. So this is the joint work with Alessandro Minuzzo and Marco Radeschi. So, all right, so I'm gonna go ahead and get started. Let's see if I can. Okay, so all right. Okay, so yeah, so let me start with what's rational homotopy theory, kind of remind people of that, introduce it if you don't if you're not familiar. So we start with some basic topology like homotopy groups. So we start with topological space X. Okay. Right. And then we can define the higher homotopy groups, pi k of X, right, as essentially homotopy classes of pointed maps from the k-sphere to your space X. Um, and we're very familiar with the pi 1, the fundamental group, but here we're going to be concentrated on the higher ones. So if you look at k bigger than or equal to 2, then unlike pi 1, this is always a billion. And unlike pi 1, it's also kind of harder to compute. Specifically, this being a billion group, you have like torsion part and free part, assuming it's a reasonable enough space that you have a finite generation. But the torsion can be very hard to compute. Um, and sometimes, so like the free part is easier to compute in general. And one way to isolate just the free part of your abelian group, the homotopy group, what you do is tensor with the rational numbers, right? And so this is called rational homotopy theory. That's, very, very hand wavy definition of what rational homotopy theory is. Um, so this is some result here, trying to illustrate this idea that sometimes the free part is much easier to compute um, than the whole homotopy groups. So this is a result of Serre from 1951. So this predates rational homotopy theory, but I guess it was kind of an inspiration, right, to rational homotopy theory, like a precursor theorem. It computes the rational homotopy groups of the spheres. So they're very simple. You have to divide up between odd dimensional and even dimensional spheres. So if you have an odd dimensional sphere, then the only homotopy group that's non-trivial would be the one in the dimension of the sphere itself. And for odd, then you also have an extra one in almost twice the dimension of the sphere, twice minus one. Right? So for example, for S2, you get that pi 3 also has pi 3 tensor Q is also Q, and this is generated by the half map from S3 to S2. So the main thing we're going to concentrate on this talk regarding rational homotopy theory is the notion of rationally elliptic and rationally hyperbolic. And for this, we're going to have to restrict a bit further type of spaces we're talking about. So this will be, for me now, a finite CW complex. And I'm going to assume also that this is simply connected. Okay, you can do some rational homotopy theory for non-simply connected spaces, for certain non-simply connected spaces, but more complicated. And for this talk, whenever I talk about rational homotopy theory of anything, that thing is going to be simply connected. So we define such a space to be rationally elliptic if you look at this rational homotopy groups and they are zero after a certain point. Okay, so they're only non-zero for a finite number of values of k. And you define rationally hyperbolic to be that the dimensions of the rational homotopy groups, when you add them up to k, that grows exponentially in k. All right, so the way I'm giving the definition, of course, it's not clear at all that these are the only two possibilities, right? There could be something in between, but there isn't, and that's the so-called elliptic hyperbolic dichotomy, right? So the very first fact here is that every space is either rationally elliptic or rationally hyperbolic. So all the rational homotopy groups either stop or they continue growing exponentially. Nothing in between. For us, we're going to be using an alternative definition in terms of the homology of the loop spaces, of the loop space of X. So if you take the loop space of X, omega X, and now we're going to look at the sum of the Betti numbers up to K of the loop space with rational coefficient, then it turns out that you can tell if the original space X was rationally elliptic or hyperbolic by the growth of this new function. So it either grows, it goes at most polynomially, exactly when the original space was elliptic, and it grows exponentially when the original space was hyperbolic. So this is what we're going to be using later on when we couple this stuff with Morse theory, right? Okay, and I'm going to keep going, but as usual, feel free to stop me, ask questions if you want. Let me use some examples. So what are some examples of rational elliptic spaces? Well, spheres, straight from Serre's theorem from the previous slide. You only have either one or two non-zero values of pi k tensor q, so that's elliptic. More generally, any homogeneous space will also be elliptic. Cohomogeneity 1 manifolds are also always rationally elliptic. This is the theorem of Grove and Halperin, 1987. You have a double disk bundle decomposition that gives that it is rationally elliptic. So reminding everyone, cohomogeneity 1 means there's a group acting such that the quotient is an interval. So it's like one-dimensional, and the interval would be the more interesting case. Okay, we're going to be concentrating on rationally elliptic things, but I'll also give you some examples of rationally hyperbolic spaces. So if you take the wedge product of two spheres, that will be rationally hyperbolic. And if you take a manifold that's not rational homotopy equivalent to a sphere, and you take a large enough number of that and they connect sums, that will also become rationally hyperbolic eventually. So that's another example. Okay. All right. So this is a talk about geometry. So let me tell you the main link between rational homotopy theory and geometry and curvature and so on, which is the Bott-Grove-Halperin conjecture. It's going to be the same kind of main motivation for the results here. So the conjecture says that if you have a closed implemented manifold and if it admits non-negative sectional curvature, then it's rationally elliptic. Or a bit more generally, if it admits almost non-negative sectional curvature. So this is when you have a sequence of metrics where the diameter is bounded and the minimum of the sectional curvature is converging to some number that's bigger than or equal to 0, then the space should be rationally elliptic. So this is the conjecture. This is open, and here are some remarks about this conjecture. Compact homogeneous spaces always admit non-negative curvature, and we saw before they're also rationally elliptic, so it's all kind of making sense. And homogeneity 1 spaces don't necessarily admit non-negative curvature, but they do always admit almost non-negative curvature. And this is Schwarzhofer and Tushman. And so that's also kind of making sense. And this is in terms of examples, let's say, and in terms of like consequences, what kind of consequences would this conjecture have if it were true? It turns out that it is true. Well, being rationally elliptic has a lot of consequences. So I'll just give one example. Rational elliptic spaces always have no negative Euler characteristic. So if you combine this with the conjecture, let's assume it's true, then you would get that non-negative sectional curvature implies non-negative Euler characteristic, and that is one of the Hopf conjectures, right? So this tells you that the Bott group Halperin conjecture is stronger than that Hopf conjecture, right? But there's a lot of other consequences, things that would follow from the Bott group Halperin conjecture. Here we're going to concentrate on a result of Joe Yeager. I believe that's his thesis work from 2012, and then a follow-up paper with some strengthening of it by Grove, Wilking, and Yeager from 2019. So this looks at the case of homogeneity 2, right? So homogeneity 0 and homogeneity 1 are always rational elliptic, and they also always admit a negative curvature or almost a negative curvature. So there's much to say there. So the next case to look at would be homogeneity 2. So their theorem says that if you have homogeneity 2 manifold, so you have a group acting on the manifold isometrically, this is a Riemannian manifold, and you have the quotient has dimension 2, then the total space M. And if the total space M has almost a negative curvature, then you get rational ellipticity, right? So you can say that this falls into the Grove, so-called Grove program, right? The Bott Grove Halperin conjecture. It's a conjecture about non-negative curvature. It's too hard, so let's add some symmetry to it. And this is a solution of that conjecture under the additional symmetry assumption that you have a group acting with homogeneity 2. Okay. So the kind of starting point for this project was a conjecture that was made in the same paper, which kind of follows naturally from the way the theorem was proved. And it says that if you have a group acting isometrically on a manifold and assume that the quotient is isometric to a hyperbolic polygon, okay, so two-dimensional hyperbolic polygon, then M is supposed to be rationally hyperbolic, okay? So it's natural to conjecture that by the way that the theorem was proved, but maybe I won't get too much into detail on that. So that's like the center thing in this project. Okay, so we can describe this like in only a few words. This project of ours that we talked about today can be described as, okay, we looked at this conjecture and we found some counterexamples, and then we also found ways of quote unquote fixing the conjecture by adding some additional assumption in which you do get that this is true. We prove a bit more than that, but in a nutshell, that's what this talk today is about. All right. Okay. So let me start with a description of a counterexample. So we found a couple of different counterexamples, but I'll describe to you like the simplest one to describe. And this starts with a Wu manifold. So-called Wu manifold is a 5-dimensional manifold given by SU3 modulo SO3. And let's put the normal homogeneous metric on it. Okay. So it's a fact that this is a rational homotopy sphere. Okay. It's not a sphere like the diffeomorphic to sphere, but it has the rational homotopy type of a sphere. And you still have an action on it, homogeneity 2 action on it. So SO3 acts on this also by left multiplication. And if you look at the orbit space of that action, of SO3 on the Wu manifold, it is flat. It's a flat equilateral triangle. And the vertices of that triangle correspond to fixed points under this action. So that's the starting point. The construction itself of the counterexample is you take two copies of the Wu manifold and you make a connected sum. Now you have to make the connected sum at fixed points. Then since the isotropy representations are the same, they're isomorphic, you can do this connected sum equivariantly in the sense that the group SO3 still acts on this manifold. And what's the quotient, right, of this new action? It ends up being a quadrangle with angles pi over 3 at the 4 vertices. And in particular, it admits a hyperbolic metric. So, then you can take that metric. So this is actually a polar action, right? So you can use actually my thesis result, and you can lift that metric on the section to a G-invariant metric on the whole of M. So you can end up with an actual isometric action such that the quotient is hyperbolic. And since the Wu manifold itself was rationally elliptic, when you take connected sum of two copies of it, it's still it's rationally, yeah, it's a 5-sphere, right? Rationally. So take connected sums of spheres with spheres, you still get spheres rationally. So this is rationally elliptic in particular, right? Okay, so now let me show you a very high-tech picture of the construction. So this is what's happening in the quotient. Okay, so on the left you can see the two copies of the quotient, right, of W by SO3. These are two equilateral triangles. We're gonna make connected sum at two fixed points in the quotient. They correspond to vertices. So what you end up getting as a quotient is the connected sum of those two triangles at a vertex. Okay, so on the right you see the quadrangle that you get, and then you change the metric to make that hyperbolic, right? So that will be one of the constructions of the counterexample, right? So, right. Okay, so now let me tell you our main theorem, which is a way to which it will imply as a corollary some kind of version of the conjecture with an additional hypothesis, right? So here is the theorem. We look at a simply connected closed Riemannian manifold. We take a group acting on it by isometries, and we're going to assume that the quotient is isometric to a good orbifold without conjugate points. Okay, so for example, a hyperbolic polygon would fit would be an example of this. And then this is the additional hypothesis that we need to add to make things work. So there's a few different versions of this. I'm going to call this property P. And I'm going to, so there's let's say two different things. Either the principal isotropy group has an odd number of connected components, or the principal orbit has first cohomology with Z2 coefficients equal to 0. Okay, so this would be this extra kind of technical condition we need to add to make things work. So once you have all of that, the conclusion is that the total space is rationally elliptic if and only the quotient is flat. It just has zero curvature. Okay, so this would be the main theorem that we have. I'll just point out some more or less obvious things that imply condition P, right? Just to kind of give a feel. Of course, if the principal isotropy group is trivial, it has one connected component, and 1 is an odd number, so that would you would be in that situation. If the group that's acting is abelian, actually that implies that the principal isotropy group is trivial, and therefore you're also in a situation where you can apply this theorem. So it works for any abelian groups acting. And of course, if the principal orbits are simply connected, definitely their first cohomology with coefficient is 0. So that would also imply condition P. So you can also be in that theorem. Okay. Again, if anyone has any questions, feel free to ask. Just jump in. All right. So how does that imply, like let's say a version of the Grove-Wilking-Yeager conjecture? Right. So if you have a group that acts such that the quotient is a hyperbolic polygon, and you have this extra condition P, then M is rationally hyperbolic, right? So that's because, hyperbolic polygon is a good orbifold without conjugate point, and it's not flat. So the M has to be hyperbolic, rationally hyperbolic, right? So it implies that. That's like kind of the main motivation for that theorem is this corollary right here. And I'm going to add some more remarks here. So first of all, the counterexample I gave earlier, of course, cannot be, the theorem doesn't apply to it, right? And indeed, you can see what the principal isotropy group and the principal orbits are, and they do violate that condition P, right? So you have Z2 squared for the principal isotropy, SO3 over Z2 squared for your principal orbit. So condition P is not satisfied, as it shouldn't. Another remark that I wanted to say is that this condition, the other condition, right, that the quotient is a good orbifold without conjugate points, is equivalent by work of Litvak and Thorbergson to the action being variationally complete. So we're going to use that later on in the proof. So this is a natural class of actions
Ricardo,
introduced by...
Can I ask a question from you before you go
on? Of course.
I forget what the principal isotope group is for the SO3 action on the Wu manifold. What's the principal isotope group? Does it violate P or not?
Yeah, there's Z2 square.
That's what I thought. So it violates P.
Yes, exactly. It violates
P. You can't apply that to give a counterexample? Or was it a different argument?
Right.
I forget now.
No, so the counterexample is that 2 copies of the Wu manifold, right?
Sure.
Maybe I go backward. Right. So
which has the same principal isotopy group?
Yes, which is Z2 squared.
Yes.
It's a counterexample because it's hyperbolic, the quotient is hyperbolic, but the total space is rationally a sphere. So it's rationally elliptic, right? That's why it's a counterexample.
Okay. Sorry,
right.
Sure. No.
Yeah, no, sure. Yeah, of course. Okay. Yes. So right. So variationally complete action, right, is equivalent to the quotient being orbifold without conjugate points, and variationally complete was like defined by Bott and Samuelson. So this is this is an important class of actions. And the other thing is I'm talking in this whole talk, I'm just talking about group actions, but in fact the theorem holds for more generally for singular manifoliations. There it doesn't make sense to talk about the principal isotropy group, but so this condition P needs to be a condition on the principal leaves. So for example, saying that they're simply connected and rationally elliptic. So you have to add that too. Orbits are always rationally elliptic, but in this more general situation, you have to add that as a hypothesis. Then you get the same theorem. But this is just a remark. I'm going to just talk about group actions for simplicity. Okay, so the rest of what I want to do in this talk is give an idea of the proof. Okay, so I'm going to start talking about the proof now. So the theorem was like equivalence, right? But let's concentrate on one of the implications of the if and only if statement. And this is the more interesting, the harder one, is this one. So okay, so let's concentrate on this. So I just kind of rewrote the theorem here just so that you guys don't have to go back and remember it. So I'm assuming rational elliptic manifold with a variationally complete action and condition P, this condition on the principal isotropy group or the principal orbit. Then we want to conclude that the quotient is flat, all right? So I have put rational elliptic in bold because in this slide that I'm about to go through now, that's the hypothesis that's going to be used, okay? So this first part of the theorem is, of the proof of the theorem is like purely topological, let's say. So here's what we're going to do. We're going to fix the principal orbit L, and we're going to fix a principal point that's not on L, okay? Then I'm going to look at the space of paths that start at the point P and end at this principal orbit L, okay? Then there's this thing called the Puppe sequence of vibrations or iterated vibrations sequence. So you start on the right-hand side there with the inclusion of the leaf of the orbit, sorry, L into M. And so that's not a vibration, but it's like up to homotopy, it's a vibration. And it's a vibration with fiber exactly the space omega PL of paths from P to L. Okay, so this is standard thing you do in topology. You modify maps by homotopic equivalent spaces and homotopic maps, and to make it a vibration. And then it continues. Then the next map, omega PL to L, is itself up to homotopic equivalence, a vibration with fiber, the loop space, omega M. And then that map is also a vibration with fiber omega L, and so on. That sequence goes on indefinitely to the left. And what you see is just like iterated loop spaces. Okay, so the next one would be like the loop space of omega PL, and then the double loop space of M, and then the double loop space of L, and so on. So we have the whole sequence, but we're only going to look at one part of it, and we're going to look at the that part from omega PL to L as a vibration with fiber omega M. Okay. Then what we're going to do to that vibration is apply the Serre spectral sequence to it. Okay. Right. So this computes the homology, right, or the of this space, of the space in the middle in some sense from the spaces, right, L and omega M. Now we're going to use the hypothesis that M is rationally elliptic, and according to our alternative definition involving the loop space, we have that the sum of the Betti numbers of the loop space omega M grows polynomially in K. So that's what we're going to use here. Then we're also going to use the fact that L, which is our principal orbit, being homogeneous space, it has it's like, well, being a compact space, actually, it's not really about being a homogeneous space. It has finite dimensional homology. Okay, so if you remember the Serre spectral sequence, right, on the second page, you see here we're doing everything over Q, so you can think about the tensor products of the homology groups with Q coefficients of the fiber and of the base tensor together, right? This gives you a grid, and that is the second page, right? And then what do? You have these maps, right? These differentials, and you take homology, and you get a third page, fourth page, etc. And in the limit, you get something that converges in some sense to the homology of the total space. Okay. Now we're starting with the hypothesis that the base has finite dimensional homology, and the fiber has exponential polynomial growth in the homology. So already on the second page, you get polynomial growth there on the second page. And what happens from page 2 to page 3, etc., is that you're taking homology of things. So the dimensions go down, right? So at infinity, you also have polynomial growth of the Betti numbers of the entries, right? And you take sums along diagonals. So you end up from this with the conclusion that the Betti numbers, the sum of the Betti numbers up to k of the space omega PL of paths, that grows exponentially. Sorry, polynomially in k. All right. So that's the first step of the proof is this, right? Okay. So let's move on. So now the next steps in the proof is where Morse theory is gonna come in. Now, for convenience, I just include the statement again that we're trying to prove here, right? We're in the middle of proof of this statement here. And now I have highlighted condition P because that's the condition that's going to be used in this slide, all right? We have already used rational ellipticity. Now we're going to use condition P. And also let me record here what we just got from the previous slide, which is that the Betti numbers of this omega PL space, this space of paths from P to L, that grows polynomially in K. All right. So what we're going to do here is use Morse theory, right? So far we only use like purely topological results, and we got some information about the topology of omega PL, but there's another path, right, to get information about this space, and that is look at the energy functional. So we're going to use the call the energy function E, and so Morse theory is about looking at critical points and their index, right? So what are the critical points of the energy functional for the spats? They're exactly the geodesics that start from the point P and arrive normal to L, okay? Now, the condition P, so what it does for us is imply that this energy functional is perfect, okay? Where I'm going to remind you what perfect means, right? So all the Morse inequalities are equations. And it also means that you can compute directly the Betti numbers as number of geodesics with that index. So yeah, I'm kind of sweeping a lot under the rug here in terms of how do you get condition P implying perfect Morse function. We'll just say a few words about this. One of the main ways, or maybe the main way of showing that Morse function is perfect is by constructing so-called completing cycles. And here we use this Bott-Samuelson cycles. So these were introduced in the original stuff we bought in Samuelson. And it was developed later for singular manipulations and so on. And so we used that construction, okay? So the Bott-Samuelson cycles, they are certain completing cycles. So they're like, for each critical point, so each geodesic with index I, you have an I-dimensional manifold inside the space, omega PL, which kind of completes the cycle. The only thing the only thing you need to prove to get perfect is that these Bott-Samuelson cycles are orientable over Q. And that's what this condition P gives you, okay? All right, maybe I won't go too much more into that. But what do we get out of this? Well, we had polynomial growth for the Betti numbers of the space omega PL. And we have just found out that there's a perfect Morse function on it. So those Betti numbers are just the number of geodesics with that index. So what we get out of this is that the number of geodesics with index at most k grows polynomially in k in that space, omega PL. Okay, so now we have a more geometric conclusion, right? Okay. So let's move on to the next step in the proof. Okay, I'm calling this billiard in the vial chamber. So And here, again, for everybody's convenience, I've added the whole statement we're trying to prove here. And this time I have highlighted the hypothesis that the action is variationally complete, because this is what I'm going to be using in this slide. And then also record here what we just got from the previous slide, which is a control on the number of geodesics of certain index in that space omega PL path from P to L. All right. So how does variationally complete come in? Well, by the definition that I gave earlier, that means that the quotient n over m over g is a good orbifold without conjugate points. So we can write it as a quotient of a manifold without conjugate points, n, divided by a discrete group of isometries, right? Now, and we can assume n is simply connected, right? We just go to the universal cover of that orbifold. Now, the key thing that I didn't mention before is that this group gamma is actually generated by reflections. So that is because we're assuming that the manifold M is simply connected itself, okay? So the general theorem of Lichak and Thorbergson says variationally complete if and only if good orbifold without conjugate points. But it turns out that when the manifold M is assumed simply connected, this group is actually generated by reflections. So you have this group gamma generated by reflections. So you have a vial chamber, like a vial, vial group acting in a vial chamber, and then we can take a closer look at these geodesics and see what they how you can understand them, right? They're in one-to-one correspondence with some other objects that I just introduced. So each geodesic is in one-to-one correspondence with a billiard trajectory from the images of those 2 points, right? The point P and the leaf L, the orbit L, in the quotient. The quotient is that good orbifold there. It's a quotient by a reflection group, so it is just some vial chamber, right? And that's also in one-to-one correspondence with the elements of this discrete group gamma, okay? So you have a one-to-one correspondence between all these things, right? So we have information from our previous steps on counting those geodesics with certain index. And now we have that the geodesics are in one-to-one correspondence with these elements of the group gamma. So the next step is going to be getting some control over this group, the elements in this group gamma from the index, right? How do these things relate? But first, I'm going to show you another picture to try to illustrate what I just said here. Again, a very high-tech picture. Okay, so in this picture, you can see on the left the manifold M, all right? We're looking at a principal point P and the principal orbit L, and we're looking at all the geodesics C going from P to L, right?
Ricardo, can I ask another question? Can you go back one slide?
Yeah.
How do you know that N is simply connected?
So we just take N, sorry, N or M? We're assuming M to be simply connected.
Yes.
Yeah, N. Yeah. So N will be just the universal cover of your orbifold.
Okay, just take the universal cover. Okay, sure.
Yes.
Sorry.
Yes. Oh, thanks. Yeah, thanks. And any other questions or? Yeah, everybody, besides Wolfgang, please feel free to ask questions too. All right. So let me try to explain a bit what I wrote here in that picture, right? So, okay, so on the left, you can see the manifold M, and it has that principal orbit and the principal point P, and you see geodesics, right? Now, the quotient of M by G, so that's my pi that I wrote, is that vial chamber, right? So on the right-hand side, you can see that manifold N without conjugate points, and you have this reflection group And if you look at the fundamental domain for that reflection group, that's called a Weil chamber. That's a convex subset. And that convex subset is a rectangle for me, okay, that I drew downstairs. So if you look at that geodesic C going from P to L, if you map it down to the quotient, it's a billiard trajectory inside that Weil chamber, okay? And between the images of P and the image of L, both of which are points in the quotient. I also wrote down this like red points, which is like where you hit the walls of the Weil chamber. So in M, those are the times, right, for where the geodesic crosses a singular orbit. Okay. And on the right-hand side, you can see that these things also are in one-to-one correspondence with this element alpha in the group. So if you take pi of P and pi of L, and you take inverse images of them, you choose inverse images in the same fundamental domain in N, this is what I call P hat and Q hat, then it turns out that those billiard trajectories, they are just geodesics in N that end at a certain point, which is related to Q hat by a certain unique element of the group gamma. So as you move around the group gamma, the element alpha in the group gamma, you're selecting different Weil chambers. And when you take the unique geodesic, this is a manifold without conjugate points. So every 2 points have a unique geodesic between them. Those are exactly those geodesics in the quotient. There's like billiard trajectories in the quotient. So this is supposed to be explained in the previous slide a little bit more. All right. Okay. So now let's go to kind of the final steps of this overview of the proof. Again, I have the whole statement. And for the previous steps, we have that we have control on the number of geodesics of index at most k. That's a polynomial in k. And then we also have that these geodesics correspond in a natural way to elements in the group gamma, that discrete reflection group gamma. Okay. So how do we control the index? So take a geodesic C corresponding to element alpha, just like in the previous picture. The variationally complete, the other thing that it gives us is that the index of this geodesic C is comparable up to a multiplicative and additive constant to the word length of alpha. So if you choose a set of generators for that group, for that reflection group gamma, right? There's a reflection in the walls of the Weil chamber, and this will generate the whole group. And you write your element alpha in terms of those generators. You count the number of letters you have used as the word length. And these things are, they control each other up to multiplicative and additive constants. This is what the variationally complete gives you. Now, this group gamma is a reflection group acting on that manifold without conjugate points. But abstractly, it's a Coxeter group too. So the generators are the reflections of the walls of the Weil chamber. And then there's a lot that's known about Coxeter groups. In particular, if a Coxeter group has polynomial growth, meaning like the number of elements of word length at most k grows polynomially in k, which is what we have here, you actually have that the group is a product of a Euclidean Coxeter group, so Euclidean reflection group, and a finite Coxeter group. Okay, so virtually it's so up to a finite index subgroup, it's a Euclidean Coxeter group.
Hey,
Now the
Ricardo,
nice thing,
Ricardo,
yeah.
this is Ravi. Sorry to interrupt.
Oh,
When you
yeah.
say the Coxeter group is polynomial growth, is this is at least quadratic, right? Or what? Because hyperbolic groups have linear growth, right? So
Right. So
but maybe I missed something. Sorry.
what do you mean linear growth? No, the hyperbolic groups have exponential growth, right? Like it has the same. So
Sorry,
you have
I was thinking of something else. My mistake. I was thinking of the Dane function, which measures the. It's like an isoparametric
Oh,
function, but that's a different thing. So you're just talking about just straight up word
Yes, yes. So you take like in the word metric, right? The word length metric, you take a ball of radius k. So just count the number of elements in the group that have, and yeah, count how many of those and how does that grow with the radius k.
Understood.
Yeah. Right. Right. So the nice thing about an Euclidean reflection group is that if you look at the subgroup of translations in it, right? It's a finite index subgroup, normal, abelian group, or as a mark to z to the n, and so if you take that subgroup, you get a covering, right? So your orbifold M mod G is finitely covered by something that has fundamental group z to the n, so it's a homotopy torus, right? So we're getting very close to this thing being flat. And then you use a little bit of surgery theory, and you also get that, in fact, so this is a nice fact about homotopy tori. Every homotopy torus is finitely covered by a standard torus. So this is in some standard books on surgery theory, and so you can go to another finite cover, right? And you get a standard torus. But now we have a metric, right? Also on this whole thing, on the quotient orbifold, which was a metric without conjugate points. And so if we lift that to this finite cover, we have now a metric on a torus, on the standard torus, without conjugate points. And it's a well-known, famous theorem of Burago and Ivanov. So the conjecture of Hopf, I think, that all such metrics must be flat. Okay, so you cannot have a metric on a torus without conjugate points, except for the flat one, for the flat ones. So, and then from that we get that the orbifold itself is flat, right? Because it has a finite cover that's flat, and then that means, of course, that the quotient was flat. So that ends the proof, right? Of this overview of the proof. All right, so that's what I have for you. So thank you very much for your attention.
Thanks so much. Are there questions?
Other question. Very nice
Ricardo?
talk.
Oh, sorry. Go ahead, Carsten.
No, it wasn't a question. I was just saying very nice talk.
Oh, thank you.
Yeah.
Okay,
really
my first
nice.
comment is then very nice talk as well. Thank you. And the question I
Thanks.
have is that, so one of the crucial steps is that the NL function is a perfect Morse function. So for that, you need that the completing cycles are orientable. And that is why you need condition P. Is that where it comes in?
Yeah, that's right. Yes.
So if I use Z2 coefficients, of course, that's not necessary anymore. And it seems like your proof then implies that the Z2 Betti numbers grow at most polynomially. Is that true?
Okay, so if you just do Z2 with everything.
Yes. Because there's a more general version of the Grover-Watt-Halpern conjecture, which says that non-negative curvature implies that the Betti numbers for any field of coefficients grow at most polynomially. And this would be support for that conjecture without condition P?
Apparently, yes. I haven't honestly thought about that.
So that would be nice.
But it seems like, did we use anywhere? No. Oh. Okay, so this is nothing about rational homotopy theory anymore, right? So this is just
correct. And just Morse theory to compute the Betti numbers with the two coefficients. It's not rational homotopy theory anymore.
Right, of the loop space.
Yes.
Yeah, I think so. I think you have, under those conditions, seems like you have that. Yeah, I didn't think about that before, but I think so.
That's a nice remark. I like it.
Yeah.
So did you say anything how you get the completing cycles, the Bott cycles?
In this talk, not really. I can tell you a little bit now. So the completing cycles are the Bott-Samuelson cycles are more or less the same that were constructed by Bott and Samuelson. So you look at given geodesic, right? You look at its image downstairs, and you look at all like broken geodesics, right, upstairs that map to the same thing. So
Okay. The same as Bott.
yeah.
Okay, I remember.
Yes, yeah,
I
it's
see.
the same as the Bott-Samuelson. So yeah,
Okay.
it's an iterated sphere ends up being an iterated sphere bundle.
Yeah.
And the condition P that we have guarantees that each step that you take on that iterated sphere bundle is orientable. So by induction you get that the whole completing cycle is orientable as a manifold.
I see. Okay.
Yeah.
Thanks.
Any other questions?
Yeah, I also have a question. I kind of can you please repeat? So this condition P had this two conditions, right? One or another
Yes.
one. But there is no wait. So why two of them? So I don't. Can you repeat this part? Like
Yes.
you cannot like
Okay, let me.
to one condition of them. You need this or.
Yeah, it's I don't know if I have a great answer for that question. We just at the end of the day, yeah, sorry.
Yeah, there was a slide, right? When you highlight, we use this condition there, right?
Okay, right. Yeah, I didn't explain too much in that slide, but I can get it to that slide. Right. Yeah, I just said that this condition P implies that this is a Morse perfect Morse function because these Bott-Samuelson cycles are orientable. Yeah, I don't have a very good answer for you. Like these are two conditions that work. So we put both of them there. I could have thrown in a third one, which is that if you go from a principal orbit to a singular orbit on the codimension 1 strata, so on the boundary, right? The dimension goes down by at least 2. So that's another condition that is actually implied by one of these, but maybe not so easy to see. But in principle, these two conditions are, I don't think one implies the other or anything like that. We want something to want to get something. These are two things that work for that, and that are reasonably easy to state because they're just about the principal orbits.
Yeah, thank you.
Okay.
I was wondering if you could imagine a weaker condition than condition P, which would just guarantee that the orbit space has curvature greater or equal 0? Or almost greater or equal 0?
That would imply so.
Well,
you mean okay.
With your condition P, you conclude, and if it's variational complete and rational elliptic, you conclude that the orbit space is flat.
Yeah, assuming rational elliptic. Yeah.
Yes. Maybe making the same assumptions, but a weaker assumption than P. Is it possible that you could conclude curvature almost greater or equal 0 of the orbit space, or greater or equal 0?
So this is a space without conjugate points. So this is an orbifold without conjugate points just from the variationally complete. So I don't think you can get. You could have, right? Can you?
I don't know. I mean, maybe I don't understand P exactly, but I was just wondering. This is a very strong condition all of a sudden, right? That you force it to be elliptic, basically because of your assumption, it forces it to be flat.
Right.
Right.
Yes.
Now, I'm just wondering if you could make another assumption, not as strong as P, that would force it not to be flat, but maybe greater or equal 0, which still would be very.
Yeah. Yes. Yeah, I think that would be difficult. Because you end up with this metric on a torus. But I see. But if you don't have P, you have something weaker than P. I see. Yeah, short answer is I don't know.
Sure. No, I was just wondering because the statement in the theorem is so strong.
Yes, right. Yes. I think it's hard. Like if you don't have perfect Morse function, it's just hard to control things. In the direction that I was talking about, right?
Sure.
If you want, of course, the other direction, then you don't really need perfect Morse functions because you can only use the Morse inequalities, and that will be enough to force the space to be rationally elliptic. But in this direction that I was talking about in the overview of the proof, so elliptic implies the quotient is flat. It's hard to do away with having perfect Morse function.
Sure.
Things could cancel out in some weird way. I don't know. Yeah.
For sure. Right.
Any other questions?
Ricardo, what I said earlier reminds me of something which would be interesting. If this thing is true for Z2 coefficients, there's a theorem of, I forget who, which says in dimension 5, if the Bettian numbers go polynomially, it must agree with one of the known examples of nonlinear curvature in dimension 5. So exactly get those examples, nothing else. That will be also a nice implication.
Oh, just with Z2.
That I don't remember. I'm senile, so I don't remember all the details, but I remember something of that type that says that this condition is so strong if you do over finite fields that you get much stronger conclusions.
Okay.
But
thanks. I'll need to think more about this on my own. The Z2 thing, like this, does it really work? It seems like it does, and what you would get out of it. It seems like you get what you said, but yeah, no, I'll need to think more about this. But yeah,
I think it's Paternine who proved that. Paternine and someone else.
Okay.
Last question. So again, I'm senile, so I don't remember everything. But wasn't there some paper, maybe recent, that the conjecture is true for in the congeniality 3?
So I think
what was it? What was that paper?
Is Marco working on this? Maybe is Marco here? I think congeniality 3 case, right? But under certain extra hypothesis, maybe.
I forget.
Hello, hi, yes, hi, Wolfgang. Yes, I'm here. Yes, in homogeneity 3, when we ask like at the moment it is fairly strong. We are asking homogeneity 3 actions with the positively curved from a positively curved manifold down to a space without boundary. There is still some work going on if you have boundary in the quotient, but it's more complicated.
I see.
But yeah.
Okay, thanks.
Is that the recent paper that Wolfgang was talking about, Marco?
Yes.
Okay. So I remembered something correctly, a version of something. Thanks, Marco. Very nice talk, Marco. Ricardo, thanks a lot.
Yeah, sure. Thank you.
Yeah, thank you again. It was a wonderful talk.
Thanks.